Hey guys, and welcome back to the activity portion of lesson 1, How Fast Does the Earth Spin? I've enjoyed reading your estimates of how fast the Earth spins. And so today's activity, and I know it's a bummer that we can't be doing these together, so I'm going to be kind of annotating or talking through the activity as you guys watch them do this on the Mystery Science program. So you might see in front of you right now, there are two individuals with paper around their necks. And I'm going to explain what they have done here with the paper. And that will help us answer the questions of why the sun appears to be moving across the sky as the Earth might stand still. As we now know that the sun does not actually move across the sky, but really it's that rotation or spinning, that was our vocab word, of the Earth. And as we rotate, we are moving, so the sun actually appears to be moving, but it is not. So what you can see right in front of you, there are two people. They have red dots located to mark where they're located in California. Now, if we were doing this in our classrooms, we would, of course, mark in Wisconsin. But those two dots on the reverse side, when they turn around, you will see it's on the opposite side of, it's like if you were to put a pole right through the middle of the Earth, it would be coming out on the other side of the planet. And so, because you'll have to notice that when our side is facing, North America is facing the sun, of course it's sunny. And when we rotate, and when North America is facing behind us, you'll notice that it is dark. So I'm going to play them moving, and I'd like you just to take notice of them moving. And now one rotation, okay, so me spinning one time represents 24 hours. And you'll know that 24 hours is the number of hours that we have in one day. And so right now, you can see that they're getting ready to spin.
All right, before you start spinning, put the sun model on the desk between you and your partner. Each of you should make sure that you're now turned to face the sun. Then discuss this question with your partner.
So if the Earth is facing the sun, like you are right now, what time do you think it is where you live? So right now, you can see the dots that are on their paper is facing towards the sun. Okay, so you would expect it to be daylight. You might not know if it's 1 o'clock in the afternoon or 10 o'clock in the morning, but you know that we're receiving daylight. So this is the time of the day where we're at school or we're playing at the park on a nice sunny day. This is not an evening time.
Both of you slowly spin to the left until your back is towards the sun. Because you're pretending to rotate like the Earth on its axis, you want to make sure that you just move your feet. Don't turn your head. Then discuss this question.
Okay, and so now you can see that second red dot, which is exactly going through the center of the Earth from California, and it is somewhere there in Europe. So right now, I'm going to pause this. Right now, you can see that that person is, and the dot in North America is facing away from the sun. So what time would you expect it to be? Okay, this would be sometime at night. So it might be 8 o'clock in the evening. Maybe it's midnight and everyone is in bed. Maybe it's 2 in the morning, but these are our nighttime hours.
Now that you know how to spin like the Earth, here's your first challenge. Slowly spin to show your partner what it would look like for 3 days on Earth to go by. Make sure you take turns.
Okay, so here's what I want you to do. So you're watching this at home. I want you to stand up wherever you are, and I'm going to give you a couple seconds, and if you need more time, you can certainly pause it. I want you to spin or rotate the how many rotations it would take for 3 days to go by on Earth. Okay, so I'm going to have you do that now. Okay, if you're not really sure what to do, think about how long it took that person, or how many rotations it took that person for that dot in California that was located up on her paper. It was kind of like right here, right under her neck. So she rotated. We had, if I'm facing the sun, we have 1. Okay, that would be 1 day. 1 complete rotation is 24 hours. So that's 1 spin. I'm going to do that again. 2 spins, 2 days. And I think you could probably start to see a pattern now. 3 spins. So three complete rotations equals 3 days. So in that time, we have 3 partial days, so 3 12 hours of daylight and 3 12 hours of nighttime.
Discuss these questions.
Okay, so what did you do to pretend that 3 days went by? Did you spin 3 times? Did you spin quickly? Were you rotating slowly? How many hours did you pretend just went by? Okay, so let's think about putting our math brains on here for a second. So we know that 24 hours, 24 hours is 1 day. So if I know this is 24 hours, and then 24 plus 24 is 48 hours. 48 plus 24, 72 hours. So 72 hours is 3 full days. So it takes our Earth 72 hours. I'm going to get busy down here. 72 hours to rotate 3 times. I think that was 3 times. Okay, little dizzy. Did you get that? If you weren't sure on the number of hours, that's okay. But to find that, 24 times 3 would be 72 hours.
Now,
here's the second challenge. Model how the Earth spins when the sun rises where you live. Okay, so
for
let's
your
think about
second
that.
challenge. Model how the Earth spins when the sun rises where you live.
Okay, so we live in Wisconsin, the United States, which is in North America. How is the Earth spinning when the sun rises where we live? Okay, it's just the same, right? So that we know that the sun rises in the east and sets in the west. And that's sometimes why you hear that we have time zones, to kind of keep everybody on the same pace. So when it's 8 o'clock here, where we live, it's 9 o'clock in a place like New York, because they receive the sun first. So it goes from east to west. And I hope that's not backwards on your screen.
Here's what we did to model sunrise. Start where you can't see the sun model. It's night for you when you stand like this. Then slowly spin to the left until you can just see the sun. When the sun starts to come into view, that's sunrise.
Okay, so I'm going to explain that a little bit too. So, and I have a light here. I don't want to blind myself, but I want to put it just into view. I don't know if that's going to work. So if we look at her paper here, and I'll play that again, she's kind of facing this direction. And as the sun, we'll face here, as the sun, or as the Earth rotates, we are now facing towards that sun. If my camera, what I'm pointing to right now is the sun, okay, it's nighttime, 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 nighttime. Oh, it's slowly starting to have that sunrise. Okay, and then sunset is now when I can no longer see that sun.
Okay, for your third challenge, once again, model a sunrise where you live. But this time, think about this. What do you think people on the opposite side of the world are seeing? Discuss this with your partner.
Okay, and if I were here in your classroom discussing with you, I would expect students to think about this and decide, okay, if it's light in daytime where I am now, if that imaginary pole is going through the earth, what are they experiencing? And what do you think? I want you to answer that in your minds right now. So if it's daylight here, and I might expect you guys to be watching this maybe 10:30, 11, 12:30 in the afternoon. What are they doing over there in Europe and the other side of the world? Yeah, I think so too. I think they would be sleeping. I think it would be nighttime. When we're sleeping, what do we think? They're probably starting their day, going to school, having breakfast. When it's midnight here, I'm guessing it's lunchtime for people directly across the world from us.
Here's what we noticed. When your face spins towards the sun, your back just spun away from the sun. Watch that again. Your back is going to spin away from the sun. It goes from day to night for that side. So your backside just saw the sun set. So when sunrise is happening for one side of the world, sunset is happening for the other side of the world. Does that make sense? All right, for your final challenge, spin to model the sun rising on the other side of the world from where you live. Once you and a partner have figured out how to do this, you can go ahead and take a seat.
Okay, I think because we're not actually together doing this, I'll just discuss it. So, like they said, when we're experiencing sunrise, the other side of the world is experiencing sunset. So, if we were moving, okay, now if I'm the United States on my front side, okay, now I'm starting to experience sunset, and then my back is now starting to experience sunrise. So we rotate. It's this giant cycle that we go through every, 12 hours for daylight and 12 hours for nighttime, which equals 24 hours in one of our days.
Okay, now that you have a pretty good idea of what it's like to spin as the Earth, pretend you found another planet in a distant galaxy. The planet is called Swiftia. Discuss this question.
Okay, so I think it's funny that they named this imaginary planet Swiftia, because when we think about the word swift, it means rapidly or pretty quick. So this is where it gets kind of confusing. So I'm going to try my best to go slow. You guys can certainly pause, rewind if you need to, but so Swiftia spins twice as fast. Okay, and this is where things get kind of crazy in the classroom because kids are always spinning around. So you can stand up and spin with me. And I'm going to try my best not to be very dizzy. Okay, sorry, I think there was a pause button I was seeing. Okay, so Swiftia spins twice as fast. So that means that in 24 hours, we have one day. So how many hours do you think it would take for them to experience one day? So if this is, and I'm going to try my best to mimic these spins as as proportionate as possible. So here's 24 hours. Okay, that's a normal spinning speed for me. That's on planet Earth. Now Swiftia, okay, twice as fast. Okay, so this would be twice as fast. How many hours would that be? Okay, so another way to think about this is if someone is running a race, and let's say that it takes them 10 minutes to run the race. Okay, and this next person was able to finish that race. They were running twice as fast. Because they were running twice as fast, of course, it's going to take less time. So we think about Swiftia it's going to take less time to have a day, but how much less? Well, actually half. So what is the half of one of our Earth days? That's 12 hours. So if we had 24 hours for one day, and now Swiftia, okay, twice as fast. Yeah, I agree, 12 hours. And that's something really important. So the faster a planet spins or rotates, next time call me out on that if I'm not using those vocabulary words, right? So the faster a planet rotates, the shorter their days. So when we think about Mercury and Venus, because they have a shorter path to travel, their days are much shorter. And when we get to the distant planets, the gas giants, they have really, really long days because they have such a far distance to travel. Okay, so again, I'm going to kind of repeat this. You'll probably want to write this down. Hint, hint, you may see this on an assessment in the next couple days. So if a planet spins twice as fast as Earth, the day is only 12 hours. It's half the time of Earth days. Okay, so now what if a planet rotates a lot slower than Earth? Would you expect the day to be longer, shorter, the same? Let's find out.
Pretend you found another planet called Slow Globe. Discuss. Then be sure to watch the final video.
Okay, so Slow Globe, another tricky name, not so much, right? So Slow Globe takes 10 times as long to spin. So I'm already trying to do that math. 10 times to spin as the Earth. How long is a day on Snow Globe? So here we have 24 hours. Okay, I need to go 10 times slower. I'm going to try to do that as I explain, so listen carefully. So I'm going 10 times slower. Obviously, my day is going to take much longer. How much longer? 10 times, right? So what is 10 times 24? Yeah, 240. 240 hours in one day on planet Snow Globe. That's crazy. I wonder if any of our current planets have days that long. I bet we'll be finding that out soon.
So how fast does the Earth spin? Well, in the activity, you created a model of the Earth and the Sun. And by spinning once in place, you modeled the Earth's spin around its axis. Since a full day is 24 hours long, you know that one spin takes 24 hours. But how fast is that exactly? Like, if we were to put that in miles per hour, the way we measure the speed of a thing like a car, what speed would that be? Well, to do that, we'd have to figure out how many miles the Earth turns per hour. There are 24 hours in a day, but how many miles are there in one spin? Put that question another way. How many miles around is the Earth? The Earth is huge. Measuring it is not easy, but scientists have been able to figure out exactly how large it is. We know that the circumference of the Earth, that's the distance all the way around the equator of the Earth, is about 24,000 miles. So then we can just do some simple math. If it takes the Earth 24 hours to do one spin all the way around itself, that's 24,000 miles divided by 24 hours in one spin. If you do the math, that equals 1,000 miles an hour. Whoa, wait a second. The Earth is spinning at over 1,000 miles an hour? Now you can kind of understand why people a long time ago had such a hard time accepting this idea. If the Earth is moving at 1,000 miles an hour, why wouldn't we feel that? But as Galileo figured out, this movement is a constant movement. Everything around us here on Earth moves at this same speed. The clouds, the air, the ground, the buildings, even you as you sit there in your seat. We're all moving together.
Can you believe that? We're currently moving at a speed of 1,000 miles an hour. That is insane. That is so crazy. And we certainly don't feel it, which is something we'll discuss in later lessons. And we certainly haven't flown off of the Earth, which is, again, something we'll be talking about in a little while.
Together at almost 1,000 miles an hour, which is why we don't really notice it. Now, that said, you can notice the movement of the Earth's spin. It's not something you can feel, it's something you can see. This, what otherwise looks like the sun moving, is actually the Earth spinning. You created a model of this in the activity. As you stood with your back to the sun, you modeled nighttime for this side of the Earth, the side not lit up by the sun. But as you spun this way, now the sun appeared to move into your view, just as what happens at sunrise in the morning. As you continued spinning all the way to this side, now the sun appeared to move out of your view, just as what happens at sunset in the evening. The sun looks like it's moving, but it's really the Earth that's moving. Here's one more thing we can do to help us picture this. A globe for the Earth, a lamp for the sun, and then to represent you or me, we stuck a Lego man on the globe. We can call him Lego Man Joe. Then we filmed what Lego Man Joe would see as the Earth did one complete rotation. Let me show you. First, let's move the camera behind Lego Man Joe so we can see what he sees. There we go. Now, in a second, I'm going to start spinning the globe like this, just like the real Earth spins, but I'm not going to move the sun. Okay, let's watch what Lego Man Joe sees. Here we go.
Okay, and so now you can see, sunrise for Lego Man Joe.
That's actually...
Okay, and now we notice the sun getting
turning. Sun is
higher in the day.
Up, up, up. Earth is turning. And I'm going to turn Lego Man Joe around on the globe here so that he can continue to watch the sun.
He's watching the
now
sunrise
I'm spinning
and
the
sunsets.
globe again.
Awesome. Okay, so now the sun is starting to fade into the horizon.
Here's sunset about to happen.
Now poor Joe cannot see anything at all.
There you go, sunset. So next time you see the sunrise or the sunset, think of the Earth's rotation. It's not the sun that's moving, it's you, me, and the Earth. Have fun and stay curious.
Okay, so to summarize a couple of things. One, rotation. Okay, the Earth rotates on an axis around the sun. The sun does not move. That's a huge point that I want you to take away from this. The sun is not moving. In fact, we are moving, rotating around the sun every day. And the Earth spins, rotates every 24 hours at a speed of 1,000 miles per hour. The second thing that I really want you to understand is that the faster a planet rotates, the shorter the days. So for instance, on planet Swiftia, okay, moving twice as fast really just cut their day in half to 12 hours. Okay, what if we were to cut Swiftia's day in half? Okay, so their day is 12 hours. Okay, now I'm going to challenge myself, probably make myself really dizzy, but I'm going to cut that 12 hours in half. Okay, 6 hours. So if we're slowing it down, okay, I needed this little slowdown. If we're slowing it down, our day is going to be much, much longer. I can post some activities for you in Seesaw. There's some cool time-lapse videos of the sun rising and sun setting. The next activity for this day are going to be some of those questions that will help your teachers understand if we're getting the lesson. The good news is you can watch these videos again, you can pause, you can take notes, you can use them while you complete that assessment. All right, guys, stay curious, and I'll see you soon.